to focus on two projects: bright defects in semiconductor quantum dots and bright defects in carbon nanotubes. Since there is a chance that there will be no time to complete and acknowledge, I want to give acknowledgement to funding agencies and group members who did calculations. So on photoluminescence in quantum dots, it's Aaron Ford and Man with Cat, and for the defects in carbon nanotubes, it's Dr. Yun Han. So ideally, all good research is done in collaboration if possible, and one of the potential goals of the theory is to predict outcomes of the experiment. What we are trying to do is to, it's not very unique, it's just a way to survive. So by Born-Oppenheimer's separation splits electronic and nuclear degrees of freedom, each of which can be treated at different level of precision. And then through non-adiabatic coupling, one can bring them together and look for the processes like dissipation of energy from electronic degrees of freedom to nuclear degrees of freedom. And this dissipation gives relaxation, dephasing, and processes like that that may bring something relevant to experimental observables. And instead of using wave function, it's convenient to use density operator, and for dissipation there is a concept of von Neumann equation of motion, which is similar to it. And in the physics community, the connection between electronic and nuclear degrees of freedom is brought back often through expansion over elongations along normal modes, but there is an efficient way to connect electronic and nuclear degrees of freedom via so-called on-the-fly trajectories, which allow to assess these couplings and look for their connections. Also, there are multiple efficient theories that take care of this connection, and developers of such theory, of many of such theories, are here in the room. But one of the interesting and sometimes computationally efficient theory was designed by experimentalist Alfred Redfield for nuclear magnetic resonance, where the interaction between primary degrees of freedom and path is brought back into equation of motion through time-dependent perturbation theory. So we are trying to bring this Redfield tensor, which is just expansion of these non-adiabatic couplings, into numerical form to track the dynamics, photoexcited dynamics of several models and systems. And one can take the energies of the parameters for this Redfield equation from multiple level of theory, and one of the simplest way is just to practice density functional theory, which is not the top precision, but it will work for mid-sized systems, and it allows several tricks to deal with periodic boundary conditions and heavy elements if pseudo potentials are available. So there is little, I wouldn't say improvement, but specifics that allows to deal with photo-induced dynamics in models, in modeling materials, which includes heavy elements or radicals. So there is a need. Sometimes the news from experimental community inspire necessity to treat the situations when spin is not a good quantum number. And for materials with, as we saw in previous talk from Sean, sometimes it is important. And generally, if any atoms in the system include are elements in the model are from bottom or even mid of the periodic table, there is a chance of spin flip. And one of the standard ways to treat it is to look into the spinors instead of single component orbitals, which allow non-collinear spin. And in this treatment, it is quite natural to deal with non-conserving spin configuration at some low level, qualitative level of assessment. So if one practices on-the-fly couplings along nuclear trajectories in this paradigm, then it allows some electronic dissipation processes which do not conserve spin and may be relevant, at least for qualitative interpretation of some experiments. Another aspect, of course, excitonic effects are primary effect in many of systems, but in some cases, one can approximate or minimize influence of the excitonic effects in the following paradigm. So let's think we have some bound excitons, for example, in beta-Salpeter equation, where excited states are superposition of several electron hole pairs with some expansion coefficients. And if there is a proof, or at least a hope, that in this series of expansion coefficients, there is a leading term which is substantially bigger than other ones, then one can assume excited state as consisting of only one electron hole pair. It is not a general approach, and it is rarely available, but sometimes one can do some interesting qualitative analysis based on this approximation, and one can call it independent orbitals approximation. Also, sometimes the number of excitons, number of excitations is not constant. One example, if one looks at the recombination when we go from one excitation to zero excitations in the system, or another example, if one goes from one excitation to two excitations, if it is available by energy conservation, there are multiple exciton generation processes, and also at lower qualitative level, one can just treat it with Fermi's golden rule, just take in Coulomb matrix element if such process is allowed by energy conservation. Then why not? One can assess probability of such process and maybe get some rates. So this machinery will be applied to attempt to apply to photoluminescence in several quantum systems, including those with heavy elements when spin is not conserved, and number of excitations can change along the timeline. And one of the examples is popular wet halide perovskites with methylammonium cation. So we just tried to look on the couple of elementary processes and compare their rates, and it looks like there is a competition with several photoexcited pathways of relaxation, like radiative recombination, non-radiative recombination, the relaxation from higher excited to lower excited through energy dissipation, and simultaneously there is a change of the number of excitations from 1 to 2, just made by this Fermi's golden rule approach. And if one brings all these approaches into a so-called rate equation and assesses probability to emit a photon at each stage of time dynamics, one can get time resolved emission, or if one integrates it over time, it will be time integrated emission, which is related to photoluminescent spectrum. So by bringing all these things together, it was an attempt to compare processes in wet halide perovskite quantum dots under quantum confinement when the charge carriers are brought together as people squeezed in the elevator. They need to interact even if they don't want to. And this assessment of ultra-fast multi-exciton generation later was found in the reasonable range of the order of magnitude. So on experiment, it's something quicker than 90 femtoseconds, and on calculations it was 10 femtoseconds. So another little overview. So I didn't study the main part. It is a quick skim through. So if one takes similar type of wet halide perovskite quantum dots with cesium cation, and because of the ionic crystal nature, if one wants to consider it as a quantum dot, one needs to practice surface passivation. And since it is an ionic crystal, one of the optimal strategies is use dual ligands. So one ligand coordinates with cation, another with anion. And here we modeled alkyl ammonium, and alkyl was very short, like just 2 carbons, and short carboxylic acid, and they were passivating surface in the alternating ways so that they do not let charge carriers away from this model, so they are truly confined. And all this machinery was just applied to explore emission and comparison of radiative and non-radiative lifetimes, which was in the reasonable agreement with experiment, about 50%. Maybe it's just a lucky coincidence, but it was interesting. And behind this observation, we just looked for time propagation of the photoexcited states. So it is an independent orbital approximation, so it's independent charge carriers, but they are under quantum confinement. So orange are negative charge electrons, blue are positive holes, and as time goes by, they redistribute inside this semiconductor quantum dot. You see there are ligands around and charge carriers inside, and there is not much leak of the charge outside of this confinement. And the image is not so spectacular, but as time goes by, energy is changing, and system is exploring different states with different probability to emit light. So finally, it gives the time resolved and time integrated spectra. If instead of photoexciting, one injects a charge and then just excites it by infrared, those quantum dots can serve as emitters in the infrared range, which is a challenge because the infrared excitation is very close to frequencies of normal modes, and energy dissipates quite quick. So in this situation, if charge is injected in such model, the ions are redistributing. There is some nuclear reorganization, polar information, which changes electronic and optical properties. And one can consider formation. One can interpret what happens upon injecting charge and re-optimizing nuclear geometry induced by a charge injection as formation of progression of like hydrogen atom-like states. And later on, one can excite some of them and look for emission for transitions between these hydrogen-like states. What was interesting to observe that the excited polaron emission for negative charge injected, like negative polarons, had photoluminescence quantum yield about 3 orders of magnitude higher than positive. It's 3 orders of magnitude in comparison, but both are very small numbers. And the rationalization of this observation is that the positive polaron, the electronic states in the valence band are closer spaced, and they fall into very tight, very good resonance condition with nuclear modes frequencies. So the excitation dissipates into nuclear motion quite quick, and the non-radiative lifetime of this infrared region positive polarons is much shorter than lifetime of the negative polarons. So here is story number one that I want to spend a little bit more time on. So here is the same style of model, semiconductor wet halide perovskite quantum dot, with and without defect. So there is a common belief that defects and trap states have feature to quench photoluminescence, to be dark in their nature. And in this material, according to calculations, it's yet to be compared with experiment, but it looks like that even in presence of a defect, the quantum yield of photoluminescence is quite high. And hypothetically, it is related to polarization of this material, and it can be verbalized as defect tolerance. So the surface of quantum dots is passivated by dual types of ligands, anions and cations, which are a little longer than native anions and cations in this ionic crystal. And there is a chance that by photoexcitation, there is a photodesorption of ligands. And if they desorb, then since they are anions and cations, they can recombine back into chemically neutral molecule, leaving part of the surface of this nanostructure unsaturated, not covered by protective ligands. And the question is whether this recombination of defects will or will not make the lowest transition darker, whether the photoluminescence quantum yield will substantially degrade to lower values or will be in the similar range. And we did try arrange several types of anionic and cationic ligands, but here I'm going to tell a story only about one pair of ligands with the anion bromine and cation is alkylammonium. So just a little of technical details, and this is just ground state DFT, but with non-collinear spin that naturally allows spin fluid transitions. And one in such representation, one shouldn't worry about whether the it is singlet or triplet configurations. They all are there in some sort of a natural way. So the upper density of states is for pristine model, and the lower one also pristine model in the under charge constraint of promotion from ground to excited. Both occupied and unoccupied orbitals are localized on the inside of the structure and are expected to be bright. And if one removes the pair of ligands in the area showed in the area indicated by this dashed circles. There is an additional state on the surface trap that appears as a shallow defect close to the edge of the conduction band, and this state is a subject to be suspected to be non-emissive, or if it is not the case, it will be great. So there is a main absorption from valence to conduction band, and here one uses the notation SHSE. So it is maybe not the best notation, but if one would deal not with cubic nanostructures, but with spherical, and if one would look for angular momentum of the envelope function of these orbitals, then one could see a progression of SPD, angular momentum for electrons and holes, and the lowest states on the edges of the valence and conduction band are reasonable to denote with this in this notation. So we practice non-adiabatic couplings along the molecular dynamics trajectory at relatively low temperature in here, and the right panels show Redfield tensor slice responsible for population relaxation only. So for the pristine model, the high and low values are alternating, as typically happens in the non-collinear spin approach, and upon bringing the defect, the more and more states are involved in the transitions. So there is a little addition to this model, the inexpensive way to take into account the recombination. So although the this treatment of dynamics of electronic states keeps number of excitations fixed, but primarily all recombinations happens from the lowest excitation, and the rate of this recombination, non-radiative recombination, is known. So if one would look for solution of the densities of the populations of both in the valence and conduction band in this specific functional form, which includes the zeroth order kinetic of recombination, then it would combine together dissipation and recombination under one in one part. So it's just a little trick which is quite innocent. So here are kinetics of the occupations in this basis, and as expected from the population goes from higher energy to lower energy, but then it drops to zero because of this trick with recombination. And this trick with recombination is very important for assessing photoluminescence quantum yield. So in the following figure, there are greenish figures, bluish figure, and then integrated photoluminescence. So greenish figure shows the charge density as function of time and energy. So greenish color corresponds to equilibrium distribution, blue corresponds to the lack of electron of charge hole, and orange to excess of electron. So at time zero, photoexcitation promotes electron from valence to conduction band. As time passes by, the electron loses its energy into lattice vibration, and hole also loses its energy. And then at some time they recombine, and therefore this yellow, orange, and blue stripes are decaying and disappearing. So time when they disappear corresponds to recombination time. And then if you look onto the next bluish figure, it shows photoluminescence as a function of time and energy at different transition energies. And one can, in the panel B, top middle, there is an original emission at the same transition energy where the system was excited, and then there is a bright orange feature at like 2.2 or close to the band gap. But this emission is not eternal, is not forever. It disappears at a time when non-radiative recombination occurs. So by bringing in this time of recombination, one can maybe not very precisely, but it is from the first principle, by in the one pot in all calculations coming from the same stem and without additional approximations, to assess the photoluminescence quantum yield. So this integration over time limit, over time range, brings all probabilities to emit light at different instant of time together and generate the spectrum. So what is interesting that the lowest excitation, which in the lower panel, which corresponds to the system with a defect, has the lowest state, is not as bright as in the pristine, but it's quite bright. And lifetime of this excitation, non-radiative lifetime, is also not very short, likely because it is a shallow defect, and recombination pathway across the gap would still need to dissipate quite big quantum of energy that doesn't have any normal modes to accommodate it. And if one brings together the radiative and non-radiative lifetimes and compute this, so non-radiative just come from Redfield tensor and non-neighboring coupling, and radiative is just function for oscillator strength, like Einstein coefficient. Then it's dimensionless quantity, and for pristine is 95%, and for defects is 75%, which I wouldn't go to defend as the literal value as absolute truth, but the fact that they are quite close and the defect is quite bright is interesting, and probably related to the fact that defects in perovskites are compensated by polarization, and properties of materials are not deteriorated even if defects are available. So
you're about at 30 minutes, 5 minutes left.
Yeah, thank you, Sergey. And the second project is photochemistry and bright defects in carbon nanotubes. So if a model is promoted to excited state, and if it is a light model with potential energy surfaces having different shapes, profiles, equilibrium position, curvatures, then photoexcitation induces a rich chemistry. And there are a set of approximations that allow to treat this kind of processes in relatively cheap approach. One of the tricks is the rotating wave approximation, and another is pulse area theorem, where one can innocently replace a continuous wave by a train of pulses. And under this approximation, one can explore the behavior of a system under intense light for a long time and hope to get some qualitatively reasonable results. Okay, if you look on the night sky, there are stars, nice pictures. People use one or several telescopes, and if one compares signals from different telescopes, one can get more information because it allows to filter the noise, like sources of light on Earth, the reflected from the clouds. And the same, so to analyze it, one uses the correlation function by correlation of the signals from two sources. And in addition to observing stars, this Henbury-Brown Twiss correlation function of second order is used to assess quality of emission for the potential sources of light for quantum information processing. And for observation of stars, it should the G function at time 0 should be maximal, should be like 100%. And if one needs single photon emitters, it should be 0. So the product of intensities from one detector and another one should be 0. And there is a collaboration with several institutions with lead of Los Alamos National Laboratory, where one is trying to obtain emission from carbon nanotubes, which are known to be good absorbers but poor emitters. By setting a covalent adducts to such materials, there is a way to enhance their photoluminescence, and there is a hope to get this photoluminescence with the right properties of photons, single photon emitters. But the main challenge is that by synthesis, and it is light assisted synthesis, there is a distribution of several defects, each of which provides emission of different frequencies. So one needs to set up a selectivity. One of the possible solutions is to apply by chemical ways spin constraint to maximize pathways with one or another spin configuration, and it allows to filter, to narrow down types of emitters. So we are trying to model this process in two ways. One is to look if the aniline molecule, which is one of the reactant, can enter into photoreaction with surface of carbon nanotube and form a defect of one or another type, one or another optical property, depending on the parameters of the field. And I will show a couple of movies on this subject. And another, which will follow in a minute, is a little more conservative and cheap exploration of transition state. So you see that photo excitation disturbs system from equilibrium, and there is a first transfer of the hydrogen from this aniline to the surface, and then carbon-carbon bonds forms, and it is one type of defect. And by slightly changing parameters of the photo-induced simulation, one can get another pathway of So by slightly tuning intensity and frequency of emission, one can set different spatial relations where the hydrogen and carbon are setting on the surface of nanotube, and it drastically changes the optical properties. So after this first observation of the sensitivity to properties of the excitation, we did try to explore the transition state search, and by selecting the arrangement.
It's 30 minutes. It's 35 minutes.
Okay. One can get the main result that depending on the mandated either singlet or triplet configuration, the barriers for either one or another path are higher and lower. So it gives the way to select the product of the reaction by changing the conditions. So thanking the funding agencies and all attendees for your kind attention, and I'm done.
Okay, Dmitry, thank you so much for a wonderful talk, for overviewing so many research topics, such a great modeling effort. And I'm just wondering if anyone has questions. And I see already the first question in the chat. Islan, please go ahead. Do you want me to read
hello.
it? Mm-hmm.
Hello, Professor Klein. I'm a group member of Cherry's team, and I have a question on your, I think the second section of photoluminescence. There's a pristine band structure and defect band structure. And there is a roughly 50 femtosecond rising of LUMO in the band structure. I'm wondering if those rising thermal rising parts are included in your calculation. I think
yes.
yeah, this one. And I mean, it haven't reached the thermal equilibrium, so why we include this part into calculation?
So we do take into account the thermalization in order to generate the non-adiabatic couplings, which are key factor for non-radiative part of the process. We are tracking molecular dynamics of the model at equilibrium. So and here,
okay, got you.
There is a little detail. If we go to room temperature, it goes a little too violet for desorption of ligand. So results here are obtained at liquid nitrogen. And it is also one of the reasons why this quantum yield is quite high. So if one recomputes these results at higher temperature, room temperature, of course, quantum yield drops.
Okay. And the other question is about the peak around 175. So is that a like numerical accident, or there is a physical information there?
Can you please navigate me once again?
The same diagram, Venn diagram defect. There's a small peak around 175 femtosecond. The pristine and the defect one, yeah, here, and the 175, and there's a small peak over there.
Okay, so this is transition from valence band to surface trap.
Oh, okay. Mm-hmm.
And
okay. So
it happens like if one tries to recompute different size of the nanocrystal, different type of ligands, different functionals, qualitatively, this feature appears again and again. So I'm just showing one case, but it's a common feature.
Okay, thank you very much. Yeah.
Hello?
Yes. Can I follow? In the very last few slides, you have transition state. And I'm just curious because you seem to be propagating nicely for the excited state using all these methodologies. So I would assume that you are watching the trajectories. So my impression is that doing so, it would be hard to get the transition state. So how was it? How did you obtain?
Okay, so for transition state search, we used periodic boundary conditions and natural elastic band and NEB, natural elastic band.
So it would be standard calculation, not the dynamic calculation.
Yes, we did two types of calculation. Dynamics was just to make sure that it is in principle possible, and then to be more quantitative, we followed up with natural elastic band.
Ari, last question.
Hi, Dimitri. So I have a question about the about the polaronic transition that you showed us. In one of the first part of the talk, you showed that there is a polaron transition. And my question to you is that how do you define or describe this as a polaron transition as opposed to a standard electron hole or excitonic transition? Because for polaron, you need, this quasi-particle, you need a strong phonon mode to get coupled to it. So how do you identifying that? And that makes it a polaronic transition as opposed to an excitonic or electron hole transition.
Okay, yeah, thank you, Eric. In this part of the story, we inject either negative or positive charge, which shifts Fermi energy, and it populates either valence band, like depopulates valence bands or populates conduction band, and then it redefines a homo-lumen transition. So the lowest transition becomes of the quite low energy in the infrared region. And then we just apply same machinery as before, and non-adiabatic couplings naturally exhibit more intense values if the transition energy is in resonance with some oscillation. So the normal mode analysis and non-adiabatic couplings, they were two parts of the calculation. I can imagine one can do more typical approach in the physics community to explore the elongations along normal modes and compare the derivatives along normal modes and couplings obtained from there with frequencies of normal modes. But we just got non-adiabatic couplings for each pairs of states along ab initio molecular dynamics trajectories. And if you want to prove that it is related to frequencies of normal modes, then one needs to take these couplings and make a Fourier transforms of those. But it will be kind of post-analysis.